Hello everybody. We're still talking about the distillation of isotropic mixtures, and in this case or this example, we are solving an extractive distillation um, problem where we have a mixture of ethanol and water, which is 92 mass percent ethanol, which is kind of close to the isotropic compositions or concentration, and we want to get from it fuel grade ethanol, which is 99.5 mass percent ethanol. And we are using glycerol as the solvent for the extractive distillation, which is available with purity of 99.5 mass percent. And the flow rate of ethanol is, the feed is 200 kilograms per hour. And we have only 30 stages in the extractive distillation column, and we don't have any further information about the solvent or the reflux ratio or the specs of the column. So in this case, because we cannot use the shortcut column as we saw in the previous video, we have no option other than trying to predict the values and try to get as much as more realistic values as possible. So this is what we are gonna do in this problem. So I'm gonna go here for Aspen Plus. I define the components and define the method, which is an RTL. And here I have the temperature and pressure of the feed. I just put any ambient temperature and pressure, a little bit higher than the pressure, the atmospheric pressure. And this is the flow rate of 200 kilograms per hour, and the mass percent of ethanol is 92%. The same for the glycerol. I assume the same pressure and temperature. I put any flow rate for now, and this is something that we are gonna change in the future, but this is the initial value that I'm gonna put, just any random value of 60 kilograms per hour, and it's 99.5% glycerol, and the rest is water. And now for the extractive distillation column, we're going to see what kind of inputs that we have. So first we have 30 stages. This is an information that I know. The condenser is a total condenser because in our case, the product is the top product. So I have to condense it all, get some as a product, and the rest is the recycle or the reflux stream. It's a Qatari boiler. The valid phases are vapor and liquid, and here we are gonna go for azeotropic distillation, or the convergence is azeotropic because we have an azeotropic mixture. So it kind of makes some difference in the type of calculations, and that's why you have to tell him that the mixture that you're using is azeotropic. And now let's see what kind of output that we have here, or I mean specs that we can put here. For what we used to do is to put the reflux ratio and the distillate to feed ratios. I'm gonna do the same for now, and then we will see that in cases like this might not be the best thing to use, or the best type of inputs to use. So I'm just gonna follow the same procedure that we used before, and we will change it later when we know why we need to change it. So the distillate to feed ratio, I know that the top product that I'm gonna get here is almost 100% ethanol. It's 99.5, so it's almost pure ethanol. And I know from the inputs that the ethanol is 92% of 200, which is gonna be 184. So I'm gonna calculate quickly 184 divided by all the feed. So I have 200 plus 60, which is the glycerol and the feed. So it's gonna be 70.8%. So I'm gonna put the distillate to feed ratio as MS is 0.708, and for the reflux ratio I don't have any value, so I'm gonna put 1 for now. I might need to change it in the future, but this is just any value that I can use to just start with. For the streams, I have the top and bottom product are stages number 1 and 30. For the glycerol, it has to be in a top stage. As we saw here, it should be a stage in the top, so it can fall down, and while falling down, it meets the ethanol and water. I'm gonna put the glycerol at stage number 3, and the isotrope will be something in the bottom. I'm gonna put it as 2. You can feel free to change it to 22, 25, whatever the value, as long as it's realistic, and we will check it after running the simulation to see if this is suitable or not. For the top stage, I'm gonna put value of 1, and for the column pressure drop, I'm gonna put 0.25, just any values. And then I'm running the simulation. Hopefully it's gonna run without any issues. So it's now done. And now let's see, there are a couple of things I want to check. First, if the glycerol that I used is helping me to pass the isotrope or go beyond the isotropic composition or not. And the second is to check the profiles of the column, because this is an indication of how well the distillation is taking place, or if the column is performing well, or there are some parts that are not adding something to the distillation, and it can help me change the places, the locations of the feeds. So for the mist fractions, I can see that this is the top product, which is where the ethanol should be. And here I see that ethanol is 97.3%. So this is a good news that I have been able to go beyond the isotropic composition. So this is not what I need to reach. I want to go for 99.5, but I know that I was stuck at 94%. So this is a good indication that with the current settings, I was able to go to 97.3%. Now let's go for the second thing, which is the profiles. I want to take a look at the compositions and see if I can see the composition profile for everything in the liquid phase, just to give me an indication of what I have. So for this, I can see that. So the first thing is, or the first observation, that there is a change of the composition of at least one of the components in each stage. So I don't have horizontal lines in for all the components. And this is important to tell me that I don't have any issues with having stages not contributing in the distillation. The second thing is that you have to notice that when we have any feed stream, it has to form an obvious change in the profiles of the composition. So, for instance, I had feed at stage number 20. So you can see that when I went from 19 to 20, there was a drop in the composition of glycerol, or the concentration of glycerol and water, and a jump in the concentration of ethanol. And this is expected because I have already added a lot of ethanol and a little bit of water. The same here, I had a jump in the glycerol composition because I added the glycerol here. And for the rest of the streams, I had a drop in the ethanol and kind of small change in the amount of water. So this is expected, and this is what I should worry if I don't see. So this is good. Um, and from this I can see that the profile is nice, and it seems that the locations of the feeds are kind of good. So now I want to go for the next step, which is I want to see what I can do to change the um, purity of ethanol to reach the value that I want to do. So there are many values that I can change, or many things. So I can change the reflux ratio, you can change the distillate to feed ratio, but you're kind of stuck with the distillate to feed ratio because it depends on the amount of ethanol. We have calculated this based on the amount of ethanol that we have in the feed, and you want the feed to be almost pure ethanol. So you cannot change this value because the amount is constant. So if you change the reflux ratio, you will not see any big change in the output concentration, because this is not the parameter that has the greatest effect on the purity of ethanol. I urge you to try different things, because I did this. I'm sorry, I did this by mistake. I need to delete the internals now because I don't want to go through this. Anyway, so back to the specs. So I urge you to change anything here in the pressures. I have already done that a lot, and I don't want to waste time going through this here, because you'll find that it doesn't have that big effect on the purity of ethanol. And the factor that has a very big effect on ethanol is the amount of glycerol that we're using, and this is the point that we're gonna go through now that this 60 kilograms per hour is not the right value. It's good to help you go for 97%, but you need to add more glycerol to go for 99 point something. So I'm gonna change it to 80 or 90. Let's go for 90 and see what we are gonna get out of the column. So by running the simulation, um, we're getting an error, and this is one thing that you might be kind of confused of, or you don't feel that this is logical, but you'll see that this error, which is the material and energy balance failed to converge. uh, so this is this error tells you that there is some kind of contradiction between the inputs that you have and the kind of calculations that it's doing. And after doing some trials, I was able to understand why. So the value that you put here, 0.708, from the calculator here, it was calculated based on 184, which is the amount of ethanol, which is almost always constant because the feed flow rate is constant, and it's divided by 200 plus 60. In our case, we have 200 plus 90 now. So I'm changing the denominator in the distillate to feed ratio. So in this case, the distillate to feed ratio is not giving me the flexibility that I need um, to be able to get the amount of purity, or the purity of ethanol that I want. So using the distillate to feed ratio is based on the amount of feed that you're using, or amount of glycerol that you're using. So if I change the feed, then I have to change the distillate to feed ratio, and this is kind of tedious thing. So a better thing that I know that here the 184 is gonna be always 184. So I'm gonna go for distillate rate instead of distillate to feed ratio, and put it as mass as 184. And now, regardless the amount of glycerin that I'm gonna use, the distillate rate is gonna be constant, and the rest is gonna go to the bottom. So this is one case where using the distillate to feed ratio is not the best option. If you are keeping the feed constant, then there is no problem with this. If you are using multiple feeds and changing the feed flow rate, then this is gonna be a problem. Even if you have a single feed stream and changing the feed flow rate, then using the distillate to feed ratio either is gonna give you an error, or is gonna give wrong output, or it's not gonna give you the output that you want. So that's why in this case I'm gonna use the distillate rate and see how this is gonna help fix this error. So it's solved now, and we don't have any errors, so this is good news. And I'm gonna go back here for the stream results and see. So the ethanol flow rate, or composition, is 98.6, so it's improved. I added 50% more glycerol, and it improved the purity, or enhanced the purity to be 98.6%. So it seems that if I change the glycerol more, I'm gonna get more or high purity ethanol. But I'm not gonna do this manually, because Aspen Plus can help me do this without doing anything manually. So we did that before. I remember when we were using the heat exchanger. Um, in the heat exchanger videos, we did this before, so you can go for design specs and ask the software to change it for you. So the parameter that you are gonna monitor, or you wanna have a target value for, is the ethanol um, feed, or the purity. And the ethanol purity is gonna be stream parameter, and it's gonna be stream variable. No, it's not stream variable. Again, it's a mass fraction. Yeah, it's a mass fraction. And for the stream, the top extractor top, and the component is ethanol. The spec is here. Again, you can write the name by yourself, or you can right click and do the variable list, exactly like what we did before in Fortran, and drag it, so you don't have any issues with the spelling, or something like this. So I need the value to be 995.995, and fault tolerance to be 0.001. And the vary is gonna be the feed flow rate, so it's gonna be stream or no, it's gonna be flow rate. I think there is a flow rate here. Oh, it's a mass flow. It's gonna be mass flow. You can do something different. You can go for stream variable here, and from the stream variable you can choose the stream to be the feed of glycerol and to do the mass flow uh, in kilograms per hour. So you can do this, or you can go for the so this is the right thing to do, is to go for a stream variable and do this. But if you go for the mass flow, you can think that the mass flow, I'm gonna change the mass flow rate, so I'm gonna go for the mass flow. So the mass flow is the mass flow of a component in the stream. It's not gonna change the flow rate of the whole stream. So this is not what we want to do. We want to keep the flow rate, or change the flow rate and keep the compositions of the stream. So I'm gonna make it the stream variable, and make this the mass flow rate on kilograms per hour. I have already used 80 or 90, I think. So I'm gonna go from 80 to 100. Oops, just to have a wide range and kind of be confident that the value that I'm looking for is inside this range. And now we will run the column and see what we got. So back to the stream results of the column. It's 99.498, so it's almost 99.5%. So it has already achieved what I am looking for. The amount of glycerol that it reached is 128.50, 0.52. This is the amount that I need to reach the amount of or the purity of ethanol that I want. You can also check it from here that the manipulated was 90 in the beginning and the purity was 98.6, and when it went for 128.52, it's 99.49. It's almost 99.5. You can of course adjust the purity more if you go here for the specs and make the tolerance even smaller. um, I'm not sure if it's gonna work, but I'm just gonna give it a shot. um, yeah, I was actually very close. So it's 99.5, and there is a very small change in the floor. It's almost the same. Anyway, so by doing this, I was able to achieve what I did, and I got the ethanol to be 99.5% pure by using the extractive distillation. Um, Back here to the flow sheet, we must have something else here. We must have a solvent recovery column where we will do distillation for water and ethanol, so that we can, or water from glycerol, so that we can get the glycerol and recycle it. So this is going to be the topic of the next video, where we will see. This is going to be a simple column because the volatility of water and or the relative volatility between water and glycerol is very high. So you can very easily get rid of the glycerol and recover the solvent, so you can use it again. But the point is that we haven't done any recycle streams before, so it's going to be a very good example, or a very good thing to mention. So I'll see you in the next video, inshallah. Goodbye.